In this project, the goal is to predict the electrical power output of a combined cycle power plant using machine learning. The dataset contains 9,568 hours sensor readings collected from the power plant. Each row represents environmental conditions measured at a specific hour, along with the electrical energy output generated during that hour. The dataset includes four environmental variables: temperature, ambient pressure, relative humidity, and exhaust vacuum. The variable P represents the net hourly electrical energy output in megawatts, which is the value we are trying to predict. Because the output is a continuous numerical value, this problem is a supervised machine learning regression problem. So, coming to the code, so the model uses four environmental variables as input features: temperature, exhaust vacuum, ambient pressure, relative humidity. These factors influence the thermodynamics, efficiency of the turbines, and therefore affect the electrical power output. The target variable is P, which represents the electrical power generated by the plant. Coming to the train test split code. So train and evaluate the machine learning models divided the data sets into training and testing sets. So I used 80 by 20. Uh, 80 by 20 split, where 80% of the data is used to train the model and 20% is used for final evaluation. So that this helps ensures that the model is tested on unseen data, which gives a better estimate of real world performance. And coming to the model training, linear regression, and the random forest code. So here, the first model is the linear regression, which is a simple baseline model that ensures a linear relationship between the input features and the target variables. And the second model is the random forest, this one, which is an learning method that builds multiple decision trees and combines the predictions. So random forest is often more powerful for tabular data sets because it can capture nonlinear relationships and interactions between variables. And coming to evaluate the performance of the So I printed the output here. Coming to the evaluate the performance of the modules, I use the three evaluation metrics. The first metric is root mean squared error, which measures the average magnitude of prediction error. And the second metric is the mean absolute error, which measures the average absolute difference between the prediction and the actual values. And the third metric is the artist score, which indicates how much of the variance in the target variable is explained by the model. After comparing the models, the random forest model achieved better performance with lower error values and a higher artist score. So to validate this, So to validate the scalability of the stability of the model, I performed cross validation using the trained dataset. Cross validation splits the training dataset into multiple folds and evaluate the model across different subsets. This helps ensures that the model is not overfitting to a specific training split and the results are more reliable. Coming to this plot shows the relationship between the actual power and the actual power output and the predicted power output generated by the model. Ideally, if predictions were perfect, all points would lie exactly on a diagonal line. In this plot, most points are close to the diagonal line, which indicates that the model is able to make accurate predictions. So this chart also shows the feature importance values calculated by the random forest model. And um, And features importance indicates that how much input variable contributes to a prediction. So from this chart, we can see the temperature has the strongest influence on the on power output, followed by the vacuum, ambient pressure, and relative humidity. So, machine learning can effectively predict power plant energy output using environmental sensor data. Among the models tested, the random forest model provided the best performance, achieving strong predictive accuracy. So, this demonstrates like how machine learning can help optimize and analyze power plant operations. Thank you.